So the last call for the last speakers, if there is any speaker who is not still in the panel, please raise your hand. Okay, so we can start. So very welcome to this last session of today, but I warmly encourage you to join also tomorrow. This session will be on hydraulics and eco-hydraulics and will be chaired by Professor Michele Mossa, Daniel Hayes, and Andres Hilaire. Professor Michele Mossa is Professor of Hydraulics at the Department of Civil, Environmental, Land Building Engineering and Chemistry at Polytechnic University of Bari. His main research topics are related to maritime, river, and environmental hydraulics. Then Daniel Hayes is a river ecology and management researcher at the University of Natural Resources and Life Science in Vienna. He received his PhD from the University of Lisbon, Portugal, and the University of Natural Resources and Life Science. André Hilaire is a professor at the National Institute for Scientific Research and is a graduate school at the University of Quebec Network. He specializes in eco-hydrology and physical habitat modeling. So I will give the floor now to the chair. I will just say a few words about the organization of this session. So to the panelists, you have 6 minutes to present your poster. Please stay until the end because the question will be discussed at the end of the session. I will share your poster, so you don't have to share anything unless there are some problems. And if you have some questions, please write them in the question and answer system. Thank you very much.
Thank you, Emanuele. Can I start?
Yes.
Okay, thank you very much. Good evening, good morning, depending on where you are in the world. First of all, I would like to thank the organizing committee for inviting me to be here to chair this session together with Professor Daniel Hayes. Before starting, for the eco-hydraulics on behalf of all the technical committee on eco-hydraulics, I would like to leave the floor to Professor Andres Hilaire because there is an incoming congress in Canada on eco-hydraulics and it must leave us, and so we must change the order. So please, Andre, if you want to share your screen and give us some information about this congress, this very interesting congress on eco-hydraulics.
Thanks very much, Michele. Can you see my screen? And are you seeing the presentation? Yes, thank you. So thanks, everyone. I'm here simply to forward a message from Canada. We are very happy to be hosting the International Symposium of Eco-Hydraulics and Fish Passage this coming month of May in 2024. It's the return of the Eco-Hydraulics Conference in North America. It has been here. The last time it was here was in 1996. And we are very happy to band together with another organization dealing with fish passage. And so the title of the conference is Eco-Hydraulics and Fish Passage, Connectivity and Processes Across the Riverscape. We're going to hold a conference in Quebec City. So from the map, you can see the map of Canada, north of the United States. The little dot shows you the location of the city of Quebec. It is a UNESCO heritage site. It is one of the oldest city, if not the oldest, in North America, founded by the French and then conquered by the English in the 18th century, sorry. It is the only walled inner city in North America, completely walled. We're going to hold the venue at the Hotel Concorde, which you see on the large picture. And we're right by the St. Lawrence River. And as you can see on the right-hand side, it provides some impressive scenery with the Montmorency Falls just a few minutes outside of the downtown area. We have many sub-teams. We're going to talk about different spatial scales, looking at new tools for upscaling. We're going to talk about remote sensing, telemetry, big data. We're going to talk, of course, about fish passage, since our partners are focusing on this topic. We're going to talk about habitat connectivity. looking at thermal habitats across spatial scales, looking at the large river systems such as the St. Lawrence, but other as well, and hoping to get a few presentations on winter dynamics as well. We're also trying to include some presentations on traditional knowledge and how to include them in our analyses and model. Of course, dams and hydropower are going to be central. We're going to hold special sessions on environmental flows. We're going to look at vegetation and ecohydraulics. Of course, advances in numerical methods will be central. We're going to have sessions on stream restorations and ecosystems engineers. We're also going to hold workshops. The two ones that are planned so far is a workshop on the inclusion of fuzzy logic in fish habitat modeling. A second one will be how to construct low-cost electronic data loggers and other devices. And we're hoping to add a few more workshops before the end of the year. So far, you can certainly look up the information on our website. So it's called ISE-FP for International Symposium on Ecohydraulics and Fish Passage 2024.org. We have now, it says 168 submissions, but as of this morning, we have 196 submissions, and there's still 24 hours to go before we reach the deadline for abstract submission. So you have another day to do so. And our costs are fairly low. So we're looking at a regular registration for 800 Canadian dollars. That's less than 600 American dollars. And for students, 300 Canadian dollars. So again, relatively cheap. So we hope that will be attractive. And with this, I'd like to thank you. And I guess, well, not sure that I can entertain questions, but if I can, I will.
Thank you very much, Andre. So I warmly recommend to submit your abstracts and also to attend this congress. I don't know if there are questions on this point, because as I told you previously, Andre is going, and so is not able then to answer our questions later. Are there questions? Of course, then you can visit the website that was reported in the presentation in order to have further information. Andre, I think there aren't the questions, so thank you very much for this information. Keep in touch, because as you know, as a technical committee, we are working also for the questions that we discussed during our meeting some days ago. Thank you again.
Great. Well, thanks very much. Hope to see you all in Quebec City. Bye.
Sure. Thank you. So I think that we can start the session with the presenters. And in my list, the first one, the first presentation is entitled "The Continuous Measurements of River Action Using a New Generation of Underwater Acoustic Tomography System." So please, the presenter, okay, thank you very much. To share the screen, you can start your presentation. Thank you.
Thank you very much. So it's around, can you hear me? Hello, can you hear me?
Yes, you're audible.
Yes,
Thank you very much.
Okay, it's okay, fine.
Sorry, so it's around 1:30 after midnight in Hokkaido, Japan. So good morning, everyone. My name is Mohammed Basil Al-Sawaf. So let me start with my title. So the title is Continuous Measurement of River Flow and Flow Direction Using a New Generation of Underwater Acoustic Tomography System. So as a brief start, so as many of you know that river accurate and continuous measurement of river flow is very important, because the data is very important in water-related application design, and also to understand the river system during flood periods, etc. So one of the research applications that we are doing in our laboratory is to continuously and accurately measure the river flow using a new generation of underwater acoustic system. And this system called the Fluvial Acoustic Tomography System, or the FAT system, which had been developed by Hiroshima University. And this system actually is to some extent similar to the acoustic velocity meters. So the backbone of measurement by means of the FAT system is the time of travel time of travel. So that is to say, so in order to make measurement of river flow or discharge, what you have to do is to place at least 2 stations, acoustic stations, one in the upstream and the other one located near to the downstream, like in P1 and P2. And then for each time step or time interval, you have two informations. The first one is the cross-sectional average velocity, and the other one is the cross-sectional area. And the multiplication of these two terms gives you the discharge. However, in order to estimate the discharge directly here, you have also to add or to include the flow direction. So that is to say the streamwise flow is not necessary to be straight line. So it could be diverted either to right bank or slightly to the left bank. Yes. So for that reason, so in order to estimate the flow direction exactly and continuously, so what I did here in this study is I placed 3 systems, as you can see here, P1 and P2, and also from P1 to P3, like in triangle distribution. And then I estimated the discharge along those 2 streamlines. So by solving the continuity equation, so because we assume that the discharge along P1, P2, and also along P1, P3 should be the same. And also here, the stream should be stressed that this is a unidirectional stream. So in other words, the flow should be from upstream to downstream. So by doing this, so we can determine which case by considering the value of cross-sectional average velocity along the 2 cross-sections, P1, P2, and P1, P3, and also the cross-sectional area, A1 and A2, we can determine which case is valid. So once we can determine the case, we can calculate the stream flow direction and also the value of discharge itself. So here, as you can see on the right-hand panel, we determined first the cross-sectional average velocity along the 2 streamlines, P1, P2, and also P1, P3. And here you can see in the figure 2P, the variation or the temporal variation in the flow direction along P1, P2. And finally, then we were able to calculate the discharge by means of the path or tomography, as you can see in the figure number 2C, the black line. And then we compared by another independent record, which is the rating curve, denoted by the red line. And the error percentage seems to be that the measurement was in very good agreement with the rating curve, unless during a little bit the falling limb, there was slightly difference, maybe because the measurement were performed somewhere near to a Mendel. So maybe, or the equation itself should be improved a little bit. So to conclude, in this study, we demonstrated that the minimum number of acoustic stations to estimate the river flow direction is can be reduced to 3, which is very practical and easier. And also, in this study, we determined the new guidelines to continuously estimate the river flow direction using a triangular configuration of 3 tomographic systems. So for future step, we need to also consider different kind of distributions. For example, currently we are considering like the zigzag distribution. So this could be also vital for streams that have stringent places. Yeah, and that's all for today. Thank you for listening.
Okay, thank you very much. Daniel, it's your turn, please.
Thank you very much for this presentation. Are there any questions from the audience? If not, I'll start. So basically, so how would you continue to go on in the future? How are you applying this technology in future studies? In a sense, how are you using potential advantages that you showed or disadvantages in the next steps?
Yes, well, this experiment had been done in Hiroshima, so now I'm doing currently another experiment in or monitoring in Hokkaido. So the streams in Hokkaido a little bit different from the mainland of Japan because here it's called regions. So also the streams itself are smaller and narrower. So here we are considering different type of first of frequency. So we need here to consider high frequency because the stream is very shallow and narrow. And also we need to consider zigzag pattern because because the presence of a lot of let me see, trees or wood, because Hokkaido, maybe as you know, that is recently governed by Japan, so 150 years ago. So still the streams itself is not as developed as in the case of mainland of Japan. So yeah, this is one of the advantages, and disadvantages, for example, that still I face some problems related to velocity. So using zigzag, for example, in some places I have secondary flow, so I have a kind of negative velocity. So and this seems not logic because the effect of secondary or circulations, this make the results to be considered or improved.
Daniel,
Thank you.
if you agree,
Good.
we can have
Yes.
all the presenters, all the presentations, and
Okay.
then we can have the discussion during the coffee break and the discussion with the mentors, if you agree.
Okay, perfect. Then I'll pass it on.
No,
to-
it's okay. We can change. It's not an obligation, of course. So if
Okay.
you want, you can
Then
introduce
I'll
the second
introduce
speaker.
the next
Thank you.
speakers on the study on aeration efficiency of a gabion ware by K.M. Luxmi. I hope I pronounced that correctly. So the floor is yours.
It's K.M. Lakshmi, sir. Good evening, everyone.
Hi, we hear you. All is well.
Okay, thank you, sir. Of this presentation, my topic is study on aeration efficiency of gabion ware. Oxygen essential for both human and aquatic life. So I am using here to increase the oxygen by using hydraulic structures. And hydraulic structures are employed to improve aeration efficiency and gabion wares for this purpose to increase the oxygen. The advantages are by the ecological and environmental advantages that enhance their utility in aeration. In this current study, a comparison was conducted between the flat gabion ware and stepped gabion ware. The results indicate that flat gabion ware outperforms the stepped gabion ware. I have done these experiments in the laboratory, which has channel dimensions 0.25 meter width, 0.3 meter depth, and 4 meter length, and a transparent water tank made of acrylic sheet having dimensions of 0.87 meter cube. And model 1 that indicates a flat gabion ware, and model 2 indicates a stepped gabion ware, and other model 2 is indicating two-stepped gabion ware. I have calculated dissolved oxygen levels by using the Winkler's method, and these equations I have used. E is equal to CD minus Cu upon Cs minus Cu, where CD indicates downstream concentration of the oxygen and Cu indicates upstream concentration of the oxygen, and Cs is taking here saturation concentration of oxygen level. And the second equation I'm using 1 minus E20 equal to 1 minus E to the power F, where F is indicating exponent used to consider the temperature of that water. And here we can see a graph which indicates the relationship between the discharge and the aeration efficiency at 20 degrees centigrade temperature. And it indicates that flat gabion ware, which is model 1, outperforms the model 2 and model 3 And here I have many results. The results says that the flat Gaussian weir exhibits superior aeration efficiency compared to one-stepped and two-stepped Gaussian weir models. This heightened efficiency is attributed to the increased turbulence generated by the flat Gaussian weir, which results from its ability to produce a more robust nappe when compared to one-stepped and two-stepped Gaussian weirs. And here the conclusion. In this study, the discharge, mean size, porosity, and drop height are taken as input parameters, and output parameter is aeration efficiency. The efficiency of aeration rises with an increase in drop height. Additionally, the type of particles used to fill the Gaussian is a crucial factor for influencing water aeration because the water can pass through the weir and over the weir. Furthermore, aeration efficiency increases with a higher discharge rate. Notably, the flat Gaussian weir outperforms the stepped Gaussian weirs in terms of aeration efficiency. And these are the references which I have taken to study this aeration efficiency of Gaussian weir. Thank you, sir.
Thank you very much for your presentation. Now it's the turn of the third presenters. The title of the poster is Effect of Hydrogenerator Rotor Eccentricity on Unbalanced Magnetic Pole. Please consider that this session is also hydraulics and eco-hydraulics, so some of the presentation are very peculiar. So if you can share the screen. It's okay, you can start. Sorry, I'm not able to hear from you. Can you check your microphone, please? Sorry, we can't hear. Emanuele, can you hear?
Maybe we can go to the next presenter and then again call him at the end.
Absolutely, I agree with you. So we can go on with the other presenter. Daniel, do you want to present it?
Yes, thank you. So
You're
I would
welcome.
like to introduce David Array, who will present to us on the design and construction of a cross-flow turbine rotor fabricated with recycled polymers. So David, the floor is yours.
Okay, thank you. Hi, my name is David Aray from Central University of Venezuela, located in Caracas, Venezuela. And today, I would like to talk to you about a project which is the design and construction of a cross-flow turbine rotor fabricated with recycled polymers. So to give you a little introduction, one of the main goals of this project was to contribute with electricity generation with the cross-flow turbine as a micro generation, and also not only that, but also to contribute with reducing the plastic waste in the environment. Okay, giving a new purpose to the recycled plastics. Now, about the methods of this project. Well, for this project, we considered numerous factors. The first one was the time limitations we had. We had a really tight schedule, and we had a deadline for this project. Also, the economy. We had a really tight budget. Also, we considered the equipment availability and the material availability. So we had access to a 3D printer, and we also, in case of the material availability, we selected the PLA and PETG filaments recycled PLA and recycled PETG filaments, which are currently really relatively easy and cheap to acquire. Okay, so once we carried out the design, the hydraulic design of the rotor, the turbine, we made the CAD model of the rotor and then imported it to the 3D printer in order to fabricate the rotor. So which is the one you can see in the poster, and I have it right here. The rotor was printed in 2 parts. Okay, the disc and also the disc with the blades, as you can see. Okay, so as for the results, we measured the dimensions of the rotor in order to compare it to the theoretical dimensions that we calculated during the hydraulic design. This was also we also had as for the conclusions, it was shown that it is possible to fabricate this kind of turbine rotors with recycled plastics, and also to generate electricity with the recycled plastics. Also, this is an easy manufacture method to apply in the fabrication of this kind of turbines, and also a good surface finish was obtained. However, it wasn't let's say the optimal surface finish. And also, according to the ISO 27681 standard, the dimensions were really acceptable for this rotor. So, well, with this, I end my presentation. Thank you.
Thank you very much. So now it's the turn of, I think, Di Lollo.
Yes.
With an experimental study on the ability of aquatic vegetation to trap plastic in rivers. So by Di Lollo, Gallitelli, Aduce, Maggi, Trombetta, e Scalici. Please, Di Lollo, if you can share your screen, and you can start your presentation.
I have to share the screen. Oh, no, okay, perfect.
No, I'm sharing for you the screen.
Okay, great. So, hi all, I am Giovanni Di Lollo, PhD student at Roma Tre University, Department of Civil Engineering. Today I'm glad to have the opportunity to present to you this work. It is an experimental study on the ability of aquatic vegetation to trap plastic in rivers. So plastic pollution and its catastrophic effects on the ecosystem are a global environmental problem. The amount of plastic entering the aquatic environment annually ranges between 19 and 23 million tons, but these numbers are believed to underestimate the true amount of plastic in the marine river system. So every day, plastic debris of different size and composition are poured into rivers from industrial or civil waste, accidentally or not. They are then transported to the lakes, seas or oceans, where they begin to decompose into very small pieces and are ingested by fauna or absorbed by flora. Finally, they return to the humans through the food chain. In the last years, the idea of using vegetation has developed to limit this phenomenon. The present study experimentally analyzes for the first time the ability of submerged vegetation to entrap riverine plastics. So our proposal is to propose a green solution to limit the plastic pollution. By increasing the presence of vegetation in rivers, a good portion of debris can be blocked. Then plastics can be removed from the vegetation with an appropriate extraction or washing techniques, and then proceed with a new insertion of plants into rivers. The aims of this study is to quantify the ability of the aquatic vegetation to trap plastic and understand whether different plant biotic factor, hydraulic conditions, or debris type influence it. Two submerged macrophytes among the most common in the Asian and European rivers are used in this work, the Myrophilium spiccatum and the Potamogetum crispus. These species show a similar ecology but different structure. The Myrophilium has a long stem with pinnate leaves composed by numerous thread-like leaflets. Potamogeton instead show a flattened and branching stem with linear oblong wavy leaves. So simply put, Myrophilium has a more articulated structure with more branched and numerous leaves than Potamogeton. The river is reproduced by using a recirculating flume. With the help of two centrifugal pumps connected to a tank, it was possible to introduce a constant flow rate into the channel. And a gate placed at the end of the channel is used to vary the height of the water column, simulating different hydraulic conditions and therefore the seasonality of the river. After place the plants in the channel and wait for the steady condition of the flow, a known amount of plastic with different sizes are inserted in the stream. We use macroplastics that are pieces with lengths greater than 2.5 centimeter, mesoplastic with lengths between 0.5 centimeter and 2.5 centimeter, and microplastic with length less than 0.5 centimeter. The experiment were conducted by varying the type of the plant and with two values of the height of the water column. Furthermore, for each configuration, 3 different vegetation area densities were analyzed by varying the number of the plant stolons, and each experiment lasts 1 minute. The entrapment efficiency of the two species is evaluated through the percentage of entrapment obtained from the ratio between the number of trapped fragments and the total thrown for each the price category. As I showed here in the poster, both plants had showed a good ability to block the transport of plastic in rivers. Myrophilium was found more efficient than Potamogeton, especially in trapping microplastics, meaning that a more articulated structure allows for a greater trapping of small debris. A greater density of the plants leads to a greater amount of trapped debris. The variation in a hydraulic condition did not significantly influence the result. So, in conclusion, this study has experimentally demonstrated that submerged vegetation can be used as a trap for plastic transported in rivers. The area occupied by plants and biotic factors such as the vegetation structure influences the trapping efficiency, while hydraulic conditions do not. For a greater understanding of these, the phenomenon or the use of aquatic vegetation, in situ measurements are required. So thank you all for the attention.
Thank you a lot for this interesting talk on experiments. I would like to pass it on to the next speaker, Vishal Singh Rawat, on the effects of fortnightly environmental parameters on Etsu for your Koilia Nasus catch in the Chikungo River estuary in Japan. So the screen is shared and Vishal Rawat, you're welcome to start.
Yeah. Hello, everyone. I'm Vishal Singh Rawat. I'm from Tokyo Metropolitan University. So today I'll be talking about the topic effects of fortnightly environmental parameters on coelionaceous catch in the Chikungo River estuary. So basically this research, it focuses on determining the relationship between coelionaceous, which is it's an anadromous fish, locally known as etsofish, in the Chikungo River estuary. Chikungo River estuary, as you can see in the study area, it's in the Kyushu prefecture of Japan. It's in the southern part of the Japan. So what we try to do, we got the fish catch data from a local fisherman for a period of 11 years, from 2009 to 2020. in between, in 2012, there was no data of fish catch, but we were able to get fish catch data in other years. So, and we also monitored the environmental parameters like salinity, turbidity, temperature, water level, and discharge in that particular stretch. So basically, he fishes from 14.6 kilometers from the river mouth to 16 kilometers. That was his fishing area, where he used to fish. So in figure number 2, you can see the temporal variations of all the environmental parameters. Yeah, so I also want to say that fishing is allowed from May 1st to July 20. So this is the allowed fishing period. So we focused on this period for all the years. So in figure number 2, you can see the temporal variations of all the environmental parameters from May 1st to July 20. And you can see during the low discharge period, that is the high greater tidal influence can be seen, which allowed saltwater intrusion, which increased salinity. And also we can see during the low flow conditions, there is development of ETM, that is the estuary turbidity maximum. But during the other half, after June, or second week of the June, you can see high discharge condition occurs. So during flood discharge conditions, we can see the decrease in the salinity and the flushing of and decreased SSE. So the ETM is flushed out. So from the figure, we can see that higher amount of fish catch was observed during the spring tide. We can see like the highest catch is corresponding to all the spring tide conditions. But we can't say that, okay, a fish catch is only happening during the spring tide. So in figure number 3, we can see the relationship between the mean tidal range. So we try to distinguish different tides, the fortnightly variation with the tidal range, that is spring tide, intermediate tide, and neap tide with respect to the mean tidal range. And we can see during the spring tidal range that the mean tidal range differs from 3.5 to 4, almost 4.5 meters, and the highest fish catch can be observed at 4 meters. Also, we used generalized additive model. It's a nonlinear model. It's a generalized linear model. Sorry, it's a generalized linear model to determine the relationship in a statistical way. And we found out that during spring tide, when we check, the model showed a good correlation with corresponding to other tidal conditions. So for the conclusion, we can say that environmental parameters like temperature, salinity, and river discharge, they had a significant impact on the fish catch. Higher fish catch was observed corresponding to these environmental parameters. And also we could statistically we can say that highest fish catch can be predicted during the spring tidal conditions. That's it. Thank you so much.
Thank you very much for this presentation. Now, I would like to check if the third presenter is able to give us his presentation. The title, Emanuele, was Effect of Hydrogenerator and so on. We can check again. So, is the presenter able to give some words about this poster? Okay, Emanuele, I suggest that we go on with the last presentation, which is the number 1. Turbulence distribution in open channel flow with submerged flexible canopy. And
the last presenter asked me if he could directly share the screen because he has modified the presentation. So
it's okay for me, of course.
Yeah, Gautam, you can share.
Hello everyone. Is I am audible?
Yes.
And my screen is visible?
Yes.
Okay, thank you. So, good evening everyone. My name is Hariom Gautam and my abstract title is Turbulence Distribution in an Open Channel Flow with Some Much Flexible Qualify. In this study, we investigated the turbulence distribution in open channel flow with submerged flexible canopy. An experiment was conducted on a densely vegetated canopy to record turbulence characteristics. So, in an open channel, the presence of flexible vegetation introduces additional resistance and drag to the flow, and it also reduces the flow capacity of the flow and creates the complex flow structures. Apart from that, it also alters the velocity profiles and turbulence characteristics in an open channel flow and resulting in the change alteration in the hydrodynamics of the flow. So thus the enhanced knowledge of the turbulence distribution in an open channel flow with vegetation is important for the better management of the waterways and their environment. So for the present study, a rectangular tilting flume of 40-meter long and 0.45-meter wide is chosen for the experiment. The flow depth was 21 centimeter and the discharge was 32 liter per second. So experiment was conducted for two conditions, one for plain bed condition and another for vegetated bed conditions. So in the plain bed condition, channel bottom was smooth and there is no additional roughness in the channel bottom. And for the vegetated bed condition, a flexible canopy was placed in the channel bottom, and then the experiment was conducted. Hello. Hello. Is I audible?
Yeah, go on.
Okay, fine.
Yeah.
So in the previous study, many studies, the flexible vegetation was used for the bladed shape or cylinder shape. In the present study, the vegetation was artificial flexible plants of irregular shape and non-uniform leaf area distribution was used to mimic the natural vegetation, and it is representing the sapling type of vegetation. And the length of the vegetation zone was 4.5 meter. And the flexible vegetation was 7.5 centimeter height and having a frontal width of 4 centimeter. The mean deflected height of this flexible vegetation during the flow was recorded 5.5 centimeters, and the density of the vegetation zone was 1,111 plants per meter square. Also, the porosity of this vegetation zone was 97%, and the plant area density was 42 meter square per meter cube, and also the submergence ratio, which is basically the flow depth to the vegetation height was 3.8, and the Reynolds numbers are very high, so it is a kind of turbulent flow. So the three-dimensional velocity was recorded using ADV to measure the turbulence characteristics. So coming to the result parts, the vertical distribution of stream-wise turbulence intensity, turbulent kinetic energy, and Reynolds shear stress for plain and vegetated both are compared. So in a plain bed conditions, so these turbulence characteristics are higher near the channel bed, which is equals to Z by HB is 0.2. Here Z is the flow depth and HB is the height of the vegetation. Basically the deflected height of the vegetation. So, based on the flow condition, we can divide the flow in a two zone. One is a upper free water zone, which and a lower vegetated zone. The vegetation was present. So, so the maximum turbulence parameters are recorded at the intersection of these two layers. That means at the top of the canopy, and in the upper free water layer, turbulence was decreasing towards the free water surface, and in the lower canopy layer or vegetation layer, minimum turbulence recorded at the canal bed, and it is decreases towards the canopy top. So basically, the presence of the vegetation at the channel bottom significantly alters the vegetation, significantly alters the turbulence characteristics. In the figure 2, these results are shown like turbulence intensity, turbulent kinetic energy, and Reynolds shear stress. And also the line showing the Z by HV is equal to 1 it is the canopy top. So we can see the in the upper layer, the turbulence is decreasing toward the free surface for the vegetated conditions, and it is the maximum at the canopy interface. So this to coming to the conclusion part, this research provides relevant understanding of turbulence distribution in densely vegetated flows with high submergence ratio and having the vegetations with leaf structures, like not bladed structures, but it is having the leaf structures. It is shown in figure 1. And the fluctuation turbulence is high at the canopy top because the fluctuation of the plant leaf is highest at the canopy top. So this is from my side. Thank you. Thank you.
Thank you very much. Again, I don't know. I saw, Emanuele, that you sent a question on the chat. We can try for the last time to call the presenter of effects of hydrogen generator, rotary eccentricity, and so on. But I don't think that he or she is with us, because I think that you didn't obtain any reply. Is it correct, Emanuele?
Yeah, indeed. Yes.
Okay.
So we can go on with the questions.
So yes, we can go on with a question, with some questions. And I would like to start with the first questions, with the first presentation, which is continuous measurements of river flow and so on. And please, Emanuele, if you can share again the screen. This is a very interesting application in field. And so I would like to ask if there was the possibility to have a comparison, for example, in study between your system and the classic system, for example, acoustic Doppler current profilers or something like that. If you have checked this comparison, installing your instrumentation with the more classic instrumentation, or if you are planning to do it in the near future.
Well, thank you for your question. Actually, we did a lot of experiments on observations, and we make comparison with ADCP both, and also with HADCP system. So the verification was very good with the paths compared to the classical equation, the rating curve. So, but the purpose of this application was actually because in previous research, we depends on the ADCP itself to determine the stream flow direction. So in order to obtain the direction exactly, so we depended on the ADCP. So this time, in order to be more independent, so I just depend on the tomography itself, the path system itself. And maybe also for the next research in the future. So we would like also to map the 2D velocity currents using the tomography itself. So this is one of the applications that we are working on. Yes.
Okay, thank you. Just another question. When you write continuous measurements, do you mean, because this is really a curiosity, I think that you must have a discretization of the time for which you have your measurements. So how many measurements per time are you able to access?
Yes, in the case of this, this is automated observation. So I just set the system, and then the system each 30 seconds make measurements. So acoustic signals are transmitted through the river each 30 seconds. And now we were able also to make it around each 10 seconds. This is very important because we are considering also to measure in the case of tsunamis occur during typhoons, flood induced by typhoons. So yes, continuous means that automated, and it takes measurement every very high frequency. So 10 seconds, 30 seconds, 1 minute, and so on.
So do you think that it's possible to use this tool, this way to do these measurements also to have turbulence analysis?
Turbulence. Maybe it's possible for the future, but now I did not consider, to be honest, but I think there is a possibility. Thank you for this point. I have to consider in the future.
Okay, thank you.
Thank you.
Daniel, do you have other questions on this presentation?
On this one, not. I would, on the one hand, invite the audience
Okay, please. Okay.
to put their questions just in the chat, and we can see them and address them to the speakers. I would like to shuffle the order a bit, and actually, I would like to start one of my questions with the talk from Giovanni Di Lollo on the experimental study on how aquatic vegetation traps plastics in rivers. So 2 questions. The first one would be like, in your experimental setup, you poured plastic into the system and then measured how the vegetation traps those. So I would be, on the one hand, interested in how much plastic you poured in to get these rates, and how is that reflected in kind of plastic transportation ratios that you might see in a natural environment.
So thank you for the question. Okay, the first I understand. We use polystyrene pieces of plastic. We measured 1 gram for macro, meso, and microplastics. And then that was really annoying for the microplastic. We count all the pieces. So we put inside, at the end of the channel, we have a net, so we can block, and so the plastic are not going in the recirculating system. And then we extracted both the plants and the net, and we count them by difference we have. So we put just for a preliminary start, because we follow also for the timing of the experiment. We followed other experiment on marine vegetation, and they also put 1 gram of plastic, and the experiment lasts 1 minute. If you can repeat the second question, please.
So basically, the plastic, the amount you poured in at the top, kind of like then to create this transportation rate of plastic within the flumes, how would that relate to it's not natural, but in a sense, if I can so call it, natural plastic transportation rates, or in other way, transportation rates in natural environments?
Because we put, a lot of, especially for the microplastics, that is, it will be the topic of a part of my PhD. They came out from waste discharge, from industrial discharge. So how can I say, it's simulating a little the discharging from this, and then the moving along the path of the river.
Right. So you would say you could, the values you have on the ratio of caught plastics, you could extrapolate into real life settings.
Yes.
Okay. Yeah. And then, just out of curiosity, I know you probably didn't measure that in your experiments, but like, how long would the plastic, do you know if there are studies showing how long plastic would stay in plants before it gets more dissolved or then gets passed on or something?
We didn't finish the experiment. We are doing another set of experiment that probably I will present next year, and we put continued release of plastics, and we stop the experiment, and we make another release after 1 minute or 5 minutes, and then we will be able to count to know how much the plastic remaining trapped in the plants or moved by the river.
All right.
So for now, I don't have enough data. We saw with another type of plants that a lot of plastic also in 2 minutes leaves the plant, but was a completely different macrophytes. And we are waiting for the seasonality to find other plants of this type to reproduce the experiment.
Okay, thank you. I just saw there's one question coming from the audience regarding to asking what size of plastic can get with this vegetation. I guess it maybe refers to what size of plastic you used.
Yes, we use the three macro category of plastic. So they are, we cut this cup of polystyrene in irregular or square form. So the macroplastic, this kind of macrophytes catch well the macro and the mesoplastic, the myrophilium, also the microplastic. So the size are about 2 and 2.5 centimeter for the macro. Between we put between 1 and 2 centimeter of mesoplastic, and for what we can cut between 1 and 5 millimeter of microplastic. So this plant, the myrophilium, we saw that can catch also the microplastics. We will now try also to put, I'm gonna say, really microplastic, so they are less than 1 millimeter.
All right.
I hope I answered the question.
I think that's good, yeah. And then there was another follow-up question from another person asking, are the two aquatic plants common globally?
In the ocean, no, I can see the chat. Thank you.
Mm-hmm.
Thank you for the question. Not in the ocean, but what I'm focusing now is how to block the plastic before they reach the ocean. So this kind of plants, this kind of aquatic plants are common in the rivers and also sometimes in the estuaries of the river. So they can. The idea is to put this vegetal barrier, the green barrier, before it reaches the ocean.
All right. Thank you.
Thank you.
I'll pass it on to Michele again.
Giovanni, I have a question for you.
Yeah.
I think that this is a very interesting study, because I know that this is one of the most important topics for the pollution of rivers. And I think that this could be the first step, which is the entrapping of plastics. The second one should be the collection of this plastic. How do you think to do it? Collecting the plants directly and then to do other plants, or with divers that, how do you think that you could do the second step of the collection of this plastic that have been entrapped?
Okay, thank you. So an idea is to create this barrier and then remove the plants, usually. So we can collect these, washing these, and then now my colleagues from the Department of Science of Roma Tre University are working on washing techniques and collecting techniques. But the fact is that to take out the plants, a portion of the plants, while we are inserting new, so it will be a cycle of growing, growing, and then continue like that. This will not block all the plastic for sure, but it's doing like this could be a useful solution. So the idea is that to take out the plants, washing, and reinsert a new one, or if we can, also this plant that we took out.
Thank you. Are there other questions on this presentation? I don't think so. And so, Daniel, if you agree, we can go on the second presentation study on aeration efficiency of gabion weir, for which I would like to know if the study also involves some field experiments, or if the authors are planning to do this in the near future.
Hello, pardon, sir?
Just a curiosity, did you check also this efficiency of gabion weir in prototype scale, or only in your laboratory? Are you planning to do further experiments and also in field, so in real dimensions?
Sir, I have done experiments in the laboratory and made a model, 3 models. And to reduce that scale effects from the prototype, I have done the calculations for of the non-dimensional Buckingham pi theorem by using Buckingham pi theorem.
Okay, thank you. Daniel, or also the audience have other questions on this presentation?
Yes, let me chip one in while we're possibly